All right, so we're going to go over the Unit 3 practice test, just kind of show you the things that you should be thinking about when you're doing the Unit 3 test. So the first question here is just asking when a function is increasing, and this is just given the graph, just like what does increasing mean? Increasing means your graph is going upward. All right, so here my graph starts here and starts going up. And just knowing kind of at the peaks and valleys is when increasing and decreasing changes. So after that peak there, I'm going to be decreasing because I'm going down. That little valley there, I increase again there, and then I decrease for the rest. Right, so that's just kind of pictorially what increasing and decreasing means. And then the second thing is knowing the intervals, or the intervals you're talking about are the x intervals. So the x interval here starts at -9 and goes to -5. And you also have the other second one starts at -1 and ends at the x value 3. And you can put the little u between them. I say these are the intervals together that make up when it's increasing. That's now the more important thing, other than just looking at a graph and determining when it's increasing, is looking at an expression, a function, and being able to determine when is this function increasing or decreasing. For both these ones, we're looking at decreasing. And decreasing means your first derivative. All right, your first derivative function is less than 0. And of course, if we were doing increasing, we'd do bigger than 0. So really, we're just looking at these functions, figuring out when are they positive or negative. In this case, negative, because we want decreasing. But we care about the first derivative. So the first thing we have to do is actually find that derivative function. And so we just do our power rule. It's going to be -3x squared minus 36x minus 81. Right? So this is our derivative. And to start off with figuring when it's positive or negative, you actually start off when it's neither, which is when it's equal to 0. So the first thing I'm going to do is take my derivative function and set it equal to 0, because these are kind of the dividing points of when it's going to be positive and negative. In this problem, I can just divide everything by -3, and that's going to make the numbers a lot nicer. So if I divide everything by -3, it's going to be positive x squared plus 12x plus 27. And now I just need to factor this, x plus 3 and x plus 9. And I get -3 and -9 as my zeros. All right, so that's my zeros. So what I'm going to do now is make a number line. This goes off forever in instruction. I'm going to put these numbers on the number line in order. So -9 would be to the left, and -3 would be to the right of that. It's really important when you're doing this, you kind of differentiate what your actual zeros are. So here, I'm writing them in black, but the main thing you can do is put these like dash lines here. All right, to differentiate, these are the things that are breaking up your number line into separate parts. And then around those points, we're going to do our test points. So the left of -9, I can do -10. Between -9 and -3, do a lot of different numbers, but -4. To the right of -3, I could plug in 0. And then each of these, to find decreasing, I care about the first derivative being positive or negative. So I'm going to plug these test points into the first derivative. And the exact value doesn't make sense, but positive or negative makes sense, or is what matters. If I plugged in -10 into my first derivative, and you simplify it all the way, you'd figure out that that gives you a negative answer. And you can just plug it in and simplify. Plug in -4 into your first derivative, you'd figure out that gives you a positive answer. And you plug in 0, and that gives you a negative answer. All right, so when is my function increasing? My final answer, well, it's increasing in all the places where the derivative's negative, so it's going to be -infinity to -9 is one section, and the other section is -3 to infinity. All right, so these sign charts are going to be really important for this test, figuring out where things are positive and negative. All right, next problem, nothing changes, it's just a different function, so I got to find the derivative first. to set it equal to 0. And one thing you always want to do, like I did in the previous problem, I divided everything by -3. All right, you want to see if there's something in common. Here I can factor out a 4x squared from everything. That has to do with x plus 6. And then if 4x squared is 0, that tells me x has to be 0. If x plus 6 is 0, that tells me x is -6. And so I get these two different zeros, which I'm going to put on my number line. And actually make sure you put them in an order that makes sense. -6 is to the left of 0 on the number line. Pick some test points. And plug them in. All right, so if I plug in -10, be -400 plus 240, that'd be a negative. So I get negative in this section. If I plug in -1, it's going to be -4 plus 24, that's positive. If I plug in 1, I'm going to get 4 plus 24, that's also positive. All right, so notice it doesn't always switch. There's a lot of times, like in the previous problem, where it switches between negative and positive at each one, but that's not always going to be the case. All right, in this problem, my final answer, where is it decreasing? Just when it's negative infinity to -6. And again, make sure you're using these zeros as the ends of your endpoints, not your test points. All right, our second page, our second skill on our test is about concavity. And the first one, again, just like the last skill, is just kind of looking at a graph and determining when it's concave up. So concave up means it's shaped like a cup. If it was concave down, it's shaped like a frown. All right, so when is this concave up? All right, concave up, I just think about it as like an upward parabola. So I like to start at the valleys because all of those are concave up. All right, the hills are concave down. And they'll kind of just meet in the middle when they switch. And this one, there's no more hills or valleys, so it's going to be concave up to the end and concave up to the end. So the two red sections that I have highlighted, you can see they're like cups. That one blue section is like a frown. So what are my intervals? It's concave up from -infinity all the way to the left forever, up until that switch, which happens at about -2. It's a little bit harder to see the exact value on a graph for concavity versus increasing and decreasing. Right? But if you're a little bit off, as long as it's between that red and blue area, then you're good. And our second area starts at about 3 and goes to infinity. Right? So that's our concave up section. Again, the more important thing here is actually being able to do it within expression. Right? And the expression is we're looking for concave down. That is when our second derivative is less than 0. So the same thing we did in the first skill, we're just doing with the second derivative. So now I take my function. All right, find the first derivative first, because you can't find the second derivative without finding the first derivative. All right, just using our power rule, second derivative. And now we're doing the same sign chart thing, so the next thing is to set it equal to 0. And we only get one possible 0 here, so we're going to put that one thing on our number line, 2/3. Put a test point on the left and a test point on the right. And we care about the second derivative is positive or negative, so I'm going to plug these test points into the second derivative. If I plug in 0, I get a negative number out of the second derivative. Plug in 1, I get a positive number out. So I'm concave down when the second derivative is negative, which is from -infinity up to 2/3. Same sign chart process. It's the only difference is I'm doing it with the second derivative instead of the first derivative. And this problem is going to be the same as the previous problem. We just do it with a new function just to make sure we're comfortable with multiple scenarios. First derivative doing the power rule, second derivative doing the power rule. again, set it equal to 0 first. Again, the first thing to make these problems a lot simpler is always think about, before you start trying to factor, can you factor out a common thing? And here you can factor out a 12 from everything. And that makes this quadratic factoring part a lot easier. -4 plus 1, which gives me my two answers, x equals 4 and x equals -1. So factoring out that greatest common factor is a good trick of making your life a lot easier when you're trying to factor. And -1 is to the left of 4, so I make sure I put them on my number line correctly. Pick test points in the regions, and then plug them into the second derivative. All right, so if you were to plug in -2, again, just use like a calculator to do it quickly. Plug in -2, you would see you get a positive number. Plug in 0, you're going to get a negative number. 5, you're going to get a positive number. So I'd be concave up. That's when my second derivative is positive. So my final answer is that left region up until my first 0, and that right region up until my second, or after my second 0. Right, so that's when it's concave up. So increasing, decreasing, first derivative, concave up, concave down, second derivative. All right, our third skill is about local extrema and identifying them. All right, so this first question, all right, the graph represents the derivative. All right, that's really important. The graph is representing the derivative of the function, not the original function, but we want to know the local extrema of the original function. So, of the original function. All right, so how can we use the first derivative to find out information about the second derivative? Well, we know this thing called the first derivative test. All right, if our function goes from increasing to decreasing, it's going to create that high spot that creates a local max right there. If it goes from decreasing to increasing, it's going to create that low spot that creates a local min. Right. So you might look at this graph and say, okay, well, there's a max there, min there, max there, min there. But that's if it was the original graph. I'm looking at the derivative. So I want to see, when does my derivative change sign? Because if it changes sign, it goes from positive to negative or vice versa, I'm going to get a minimum. So when's it change sign? Well, I'm looking at 0. It happens at 3 different places. It happens at x equals 0, x equals 2. It looks like x equals like 3.75. It's not an exact number. And then are these going to be maxes or mins? All right, at 0, I switch from negative x values to positive x values, which means my original function goes from decreasing to increasing, makes that a minimum. At 2, my function values go from positive to negative. Positive to negative means my original goes from increasing to decreasing, makes that a maximum. And last one, at 3.75 goes from negative to positive again, means my original is going from decreasing to increasing, makes that a minimum. All right, so you have to use this kind of first derivative information to figure out when you have a max or min. Those are just the critical points when your derivative is 0. And then if it's going from positive to negative, it's a max. Negative to positive, it's a min. All right, how do you do that when you're not given a graph? Well, you just kind of do the same thing. You find the critical points and then figure out how your first derivative is changing. So I can find my first derivative. And then do the sign chart process we did before. So we're going to start with setting it equal to 0. Here I can factor out a 3x. I get x equals 0 and x equals -12. Put them on a number line. Pick some test points. Plug the test points into the derivative. Again, the first derivative, I'm trying to figure out the first derivative is switching, which causes that increasing and decreasing switch. So if I plug in negative 15, I'm gonna let's see, that's a positive number. If I plug in negative 1, I'm gonna get a negative number. If I plug in 1, I'm gonna get a positive number. Right. So now I know I have a my original graph. So now information about my derivative, my original graph is going from increasing to decreasing to increasing, which means at negative 12, I'm going to get a max. All right, so max at x equals negative 12 and a min at x equals 0. Right, because of that increasing to decreasing switch and that decreasing to increasing switch. The problem asks for the xy coordinate. All right, just to save time, if you plug negative 12 into your function, your original function, because that's the pair on the original graph, that's how you get the y coordinate. All right, the 0 is the easy one to plug in, you get 0, 0. So you have a min at 0, 0, you have a max at negative 12, and whatever that number would be if you plugged in negative 12. You could do problem 3 the same way, or you could do the second derivative test. So what's the second derivative test say? Is if you have a critical point with a negative concavity, that's going to give you a maximum because of this picture. I got that top right there. And if you have a positive concavity, which means you have a cup, you're going to get a minimum to that point right there. So since we're doing the second derivative test for the example, again, you could do this one using the first derivative test, just do another sign chart. The second derivative test says I can find the second derivative. Right. But the second derivative test says first it needs to be a critical point, right? Maxes and mins are only going to happen at critical points. So the critical points, I'm still going to do the same first thing of setting my derivative equal to 0. In this case, I'm going to divide everything by 3. I can factor. Oh, I can't factor. All right, I just realized why I can't factor, because I made a mistake on the derivative, which means I also made a mistake on the second derivative, so let's fix that real quick. This is 3x squared plus 12x minus 15, which makes this 6x plus 12. All right, same thing, I'm going to set it equal to 0. Oops. Factor out the 3. But now it's actually possible to factor. And I get negative 5 and positive 1. So normally now, if I was doing the first derivative test, I would make a number line and see where those pluses and minuses change. But now since I'm doing the second derivative test, I'm just interested in what is the concavity at these critical points. So I'm going to do is first plug in negative 5 into my second derivative. It's going to be 6 times negative 5 plus 12. Negative 30 plus 12 is negative 18. But the important thing, it's negative. All right, so that'll tell me information in a second. And then g double prime of 1, 6 times 1 plus 12 is positive 18. Right. So what does this tell me? It tells me at x equals negative 5, it's a critical point, and it has a negative concavity. So if we look at those concavity graphs to the left, it's negative concavity, it's a frown, which makes it a maximum. And x equals 1, it has a positive concavity, so it's a cup, and that makes it a minimum. All right, same thing, the question's asking for the ordered pair, so you'd have to take these and plug them into the original equation. All right, this equation here. All right, plug them into the original because that gives you the xy pair from your original graph. All right, that's just one extra step you can just use a calculator to do. All right, our next skill is about finding absolute extrema. So whenever you're doing absolute extrema, you are looking at the candidates test. All right, and to do the candidates test, there's two types of candidates. There's critical points. All right, and your second type is the endpoints. So you have to find these different candidates and then use them to figure out your answer. So critical points is the first one we'll do. That's where your derivative is equal to 0. So you need to find the derivative. And then set it equal to 0. As always, when you're trying to solve something equal to 0, first thing you want to do is factor out common factors, because that makes the rest of the problem easier. I get x equals 0 and x equals 3. So those are two of my candidates because those are the critical points. All right, also critical points when your function's undefined or your derivative is undefined, but that's not going to happen because we have a polynomial. And then the next thing I do is, now that I have my critical points, I'm going to try my different candidates. So I have 4 candidates. I have my 2 critical points, 0 and 3. And then I also have to do the endpoints. So the endpoints I just told, that's -2 and 4. I just want to plug these in and get my y value, whatever the smallest y value is. I'm looking for the absolute max and min. So the smallest y value is going to be the minimum. The biggest is going to be the maximum. Again, for practice in terms of doing this on the test, use a calculator. Make this part a little bit simpler on yourself rather than making a potential arithmetic mistake, even though you did all the other work correct. So when you plug these in, again, I'm just going to use a calculator. 0, if I plug in 0, I'm going to get -9. If I plug in 3, I'm going to get -36. -2, I'm going to get 39. And +4, I'm going to get -9. Okay. So again, my max is just the bigger number I get. It's the y value is 39. The min is the smallest value I get, which is -36. Again, negatives, a bigger negative is actually a minimum because it's lower on the graph. Nothing different for number 2, just making sure that you can do it consistently. So we're still going to do the same thing. Find our candidates by first finding the critical points. We're going to set this equal to 0. We're going to get 1 extra candidate, x equals 1. And then I try my candidates. We have -1 and 2 are our endpoints. 1 is our only critical point. So I put these all in to the calculator. And I plug in -1, I get -11. When I plug in 2, I get -2. And I plug in 1, I get -3. All right, so my lowest down value is the min, and the highest up value is the max. So here, the endpoints are the answer, not the critical point. Actually didn't end up mattering at all, but you need to find all of these in order to make sure that you're actually getting the correct max and min. All right, so next up, we're kind of taking a little bit of a detour. The other 4 seem really closely related. You're doing these sign charts. You're using first and second derivative to think about increasing and decreasing and all that. All right, and the next 2 kind of applications of these derivative stuff. All right, implicit derivatives are just important because not everything can be written as y equals. All right, so how can we take derivatives of these things still? All right, so we just have to remember that whenever we take the derivative of a y, we get a dy dx. So in this first problem, negative 2y squared becomes negative 4y. All right, but whenever you take the derivative of y, you're going to get a dy dx or y prime. Some people like writing the y prime, but I think I get them confused with my other y's too often. Our derivative of x is just 1, and since it's an x, I don't have to get an extra differential part. Minus 2x cubed is minus 6x squared. And again, it's an x, so I don't have to worry about anything extra. Now I'm going to solve for dy dx. I'm going to move that 1 to the other side. And I just divide to get dy dx all by itself. It's at minus 6x squared minus 1 is going to be on the top. And negative 4y is going to be on the bottom. Right, and that's the full problem for this example. Right, for question 2, same thing. The only thing we have to be careful with is that on this right-hand side, we have x cubed times y. So I have to remember to do the product rule when I get to that part. Everything else is going to be similar. Derivative of 2 is 0, so that goes away. Derivative of minus 5y squared is minus 10y. But again, it's a y, so I have to put that dy dx after it. All right, 5x squared is just our normal minus 10x. All right, but like I said, on the right-hand side, we do the product rule. So I keep x cubed the same. The derivative of y is just dy dx. Then I keep y the same. The derivative of x is 3x squared. And now the general strategy for solving for dy dx is get the dy dx is on one side and the number, or the non-dy dx is on the other side. So I'm going to move this to the right, and this term that doesn't have a dy dx to the left. So my next step is going to be negative 10x minus 3x squared y equals x cubed dy dx plus 10y dy dx. And if you move things to the opposite sides, that's fine. The important thing is the dy dx's are on the same side, so I can factor them out to the front of that expression. Now I want dy dx by itself, so I just have to divide to get my final answer. So I'm going to divide this on the other side. I get negative 10x minus 3x squared y on the top. On the bottom, that x cubed plus 10y. All right, that's the whole problem. Last one, same thing. Again, just being careful whenever you have x times y. So the derivative negative 4 is 0, so it goes away. All right, keep x. The derivative of y is dy dx. All right, plus keep y. Derivative of x is 1. That's the whole left-hand side, doing the product rule. Right-hand side, minus 4 dy dx minus 8x. I get the dy dx is on the same side. And it's just moving those two terms to where they want to be. All right, the dy dx is on the same side now, so I can factor it out. And then I can divide to get dy dx all by itself. And that's the whole problem again once you get dy dx by itself. Our last skill is the most involved one. It's basically finding absolute extrema where you have to make the equation yourself. So in this one, we have an open top glass aquarium on a square base. Its volume is 32 cubic feet. What's the minimum possible surface area for the aquarium? So I have this aquarium. and it's got a square base on the bottom. So on the bottom, the two sides are the same. It's a square base, and there's a height. So what is the surface area of this going to be? Well, the surface area, I have the bottom of the aquarium, which is s times s, so that's s squared. I have the four sides of the aquarium. Each of those is just the width times the height. And there's no top to an aquarium, right, because there's no glass there. So this is my surface area equation. I want to minimize this equation. But right now there's an S and an H, so I need to somehow get rid of that. And the way I'm going to do it is using the volume, which they gave me, which is how much it holds. So the volume is 32, and that would be S squared times H. There's two S's in my surface area equation and one H, so it's going to be easier to replace the H. So I'm going to solve this equation for H by dividing by S squared. All right, so I use that information about the volume. All right, and now H is always equal to 32 over S squared, so that's going to give me a slightly different equation. And now if you look at this equation, it only has S's. So in this equation, I can do all of my strategies for finding an absolute max or min. In this case, a minimum, because I'm trying to minimize it. I'll just do a little bit of simplifying first. 4 times 32 is 128. All right, so that is my surface area equation. I want to minimize this, so I have to find the derivative so I can find my candidate. So the surface area derivative equation is going to be 2s, and then 128 over s is the same as, write it as 128 s to the negative 1, so that's going to give me negative, when I take the derivative, negative 128 s to the negative 2. So when I actually write that in a way that's going to make it a little bit easier to solve, it's going to be minus 128 over s squared. And now I want to find, again, the critical point, so this is equal to 0. And so when I solve this, add this to the other side, multiply both sides by s squared to get rid of the fraction, divide by 2, and then take the cube root of both sides to figure out my side. S is the cube root of 64, which is 4. Right, so the minimum area is going to be when the side, the bottom, so remember S is that square bottom, is 4. And the actual question asks, what is the minimum possible exterior surface? So it's asking, what is the surface area that's going to be minimum? That's when I plug 4 into my original surface area equation. So my minimum surface area is 4 squared plus 4 times 4. And what's the H going to be? Well, over here, H is 32 over S squared. So that's 32 over 16, which is 2. Right? It's going to be 16 plus 16 times 2 is 32, which is 48. So the minimum surface area is going to be 48. Let's see, it was cubic feet was our thing, so it's going to be feet squared. And so 48 square feet of plexiglass, or sorry, it's just glass. It's going to be the smallest amount of glass I could use to make this aquarium. Next, a piece of paper is going to display 150 square inches of text. There's a 1-inch margin on the sides and top and a 2-inch margin at the bottom. All right, what are the dimensions of the smallest piece of paper that can be used? All right, so let's see what this is going to look like. I have this piece of paper, and there's margins. All right, so the actual text that I want is in here. All right, and there's a 1-inch margin on the sides and the top, and there's a 2-inch margin at the bottom. All right, and there's kind of two different ways you could go about this. You could make your variable, right, you're looking for dimensions. So you can make your dimensions the full width of the whole paper or just the text area. I'm not sure if one is better than the other. My first instinct was to make the width and the height of the text area the variable, so let's just go with that. All right, so what is the area of the whole paper going to be that I'm trying to minimize. All right, so if I'm trying to minimize the area of the paper, the area is the width, which is, let's see, the height plus 3, right? Because the whole height is here. Oops, I'm doing a different color. The whole height's here, extra 1 at the top and extra 2 at the bottom. So the whole height of the paper is h plus 3. The whole width of the paper is w plus 2. And maybe this might be a better reason to do the full width and do minus signs otherwise. But this gives me, let's see, WH plus 3W plus 2H plus 6 is the area of the full paper. But again, there's W and H's, so how do I relate W and H? Well, I know that the text part has 150 square inches of text, and that's W times H. Right, so that's one reason why having the text be the W and H is also a valid reason. The equation I'm working with has as many W's and H's, so I'm not sure which one's better to solve for. I think writing H is a little bit easier, so let's solve for W to get rid of it. And I can plug that in for my W's here. A little bit simplifying. The H's cancel there. Here we have to multiply. And I also can combine the like terms, so that's 6 at the end. I don't have to write. I can just put it there. And now this is the area that I'm trying to minimize. So now I take its derivative because I care about critical points. So the derivative of this area. 156 is going to go away. Just like the previous problem, 450 over h is going to turn into minus 450 over h squared. And 2h just turns into 2. I want to set this equal to 0. So I can say subtract 2 from both sides. I don't know why I'm writing in so many different colors. Multiply both sides by h squared. Divide both sides by 2. Sorry, negative 2. And then take square roots of both sides. Forgot that h is the square root of 225, which I'm pretty sure is 15. And I was right. So the height of that text box is 15. Now that I know where that minimum is going to happen, let me make sure I answer the question. The actual question is, what are the dimensions of the smallest piece of paper? So the full piece of paper is going to be the height. Where that text box is 15, so the full height is 18. The width, well, what's the width going to be? Width is 150 divided by h. So 150 divided by 15 is 10. So the width is going to be 10. Add those extra 2-inch margins, right? Inch margins, but there's 2 of them, is going to be 12. So 18 by 12 is the smallest piece of paper that I could make. All right, so the optimization problems, they all kind of go the same way of creating the equation that you want to minimize or maximize. In most cases, is minimize. But that equation will have multiple variables. You got to use the other relationship in your problem to relate those 2 variables, so you get a variable that has only one variable. I said the word variables a lot. But then it's just the same candidate stuff. You find the critical point, and that's going to be where your max or min happens. Most of the time, there's only one critical point, and that's the answer. If I had gotten 2 critical points for any of these, I would plug them both in and see which one's bigger or smaller if I want a max or a min. But that's the full Unit 3 practice test. I go through and make sure you know how to do all those different things so you're ready for the actual exam test thing.